Hi everyone, in this presentation I'm going to talk about the basic theories of hydrostatics of floating offshore structures. This is a bit different from the topics I normally cover here on this channel. However, hydrostatics constitutes an important branch within fluid mechanics that studies the behavior of fluid at rest. And so I would like to talk a little about this subject. In general, for a partially submerged body of arbitrary shape subject to arbitrarily large inclination angles, it is necessary to adopt a fundamental approach, which is the integration of the pressure distribution on the submerged area in order to estimate all the necessary hydrostatic characteristics. In this presentation, the following topics are covered: principal ship dimensions, basic ship hydrostatics, numerical integration in naval architecture, hydrostatic curves, statical stability at large angles of heel, simple models of stability, weight and trim calculations, flooding and damage condition, the inclining experiment, and finally static stability of floating wind turbines. Principal ship dimensions. Here we can see several figures showing the details of a ship structure. Starboard means the right hand side of a ship when looking forward. The left hand side of a ship is called port. AP means aft perpendicular. FP means forward perpendicular. T is draft. TA is aft draft, TF is forward draft, TM midship draft, LOA length overall, LPP length between perpendiculars, LOS length overall submerged, LWL length of waterline, as we can see here. How to measure the lengths between perpendiculars. Okay, this is important subject. FP is a vertical line passing through the intersection of the design waterline with the ship bow. Here we can see the case of a keel not parallel to the load waterline or waterline. Note that AP is typically defined as the vertical line passing through the rudder post as shown here. However, in case of naval ships, the battleships, it is customary to define the AP at the after end of the vessel on the design waterline as shown here in this figure. Here we can see breadth, also referred to as beam, depth, draft, and camber. Camber is used in order to make sure that rainwater and water shipped aboard will drain off easily. The baseline, shortly BL, is a line lying in the longitudinal plane of symmetry and parallel to the designed waterline. It appears as a horizontal in the lateral and transverse views of the hull surface. The baseline is used as the longitudinal axis, that is the x-axis of the system of coordinates in which hull points are defined. Therefore, it is recommended to place this line so that it passes through the lowest point of the hull surface. Then all z coordinates will be positive. T, which is a draft, is the vertical distance between the top of the keel to the design load line, usually measured in the midship plane. The difference between depth and draft is called freeboard, as we can see here. Coordinate systems. The coordinate system is shown here. The x-axis runs along the ship and is positive forward. The y-axis is transversal and positive to port, and the z-axis is vertical and positive upward. For dynamic applications, taking the origin in the center of gravity simplifies the equations. However, it should be clear that to each loading condition corresponds one center of gravity, while a point like the intersection of the aft perpendicular with the baseline is independent of the ship loading. To define the various floating conditions, that is the positions that the ship can assume, we use another system fixed in a space as x0, y0, z0. Let this system initially coincide with the system xyz. A vertical translation of the system xyz with respect to the space fixed system x0, y0, z0 produces a draft change. If the ship fixed z-axis is vertical, we say that the ship floats in an upright condition. A rotation of the ship fixed system around an axis parallel to the x-axis is called heel if it is temporary, and list if it is permanent, also referred to as lull. The heel can be produced by lateral wind, by the centrifugal force developed in turning, or by temporarily transverse displacement of weights. The list can result from incorrect loading or from flooding. If the transverse inclination is the result of ship motions, it is time varying, and we call it roll. When the ship fixed x-axis is parallel to the space fixed x0 axis, we say that the ship floats on even keel. A static inclination of the ship fixed system around an axis parallel to the ship fixed y-axis is called trim. If the inclination is dynamic, that is a function of time resulting from ship motions, it is called pitch. A graphic explanation of the term trim and heel is given in this figure. The trim is measured as a difference between the forward and the aft drafts. Then trim is positive if the ship is trimmed by the head, as we can see here in this image. Trim is measured normally in meters. Graphic description. In most cases, the hull surface has double curvature and cannot be defined by simple analytical equations. To cope with the problem, naval architects have drawn lines obtained by cutting the hull surface with sets of parallel planes. We represent the hull surface by means of lines of constant x, constant y, and constant z. Thus, cutting the hull surface by planes parallel to the YOZ plane, we obtain the transverse sections noted in this figure as ST0 to ST10, that is station 0, station 1 up to station 10, cutting the same hull by horizontal planes parallel to the base plane XOY. We obtain the water lines marked in this figure as WL0 to WL5. Finally, by cutting the same hull with longitudinal planes parallel to the XOZ plane, we draw the buttocks shown in this figure, as we can see clearly. The most important buttock is the line y equals 0, known as a center line. For almost all ship hulls, it is a plane of symmetry. Stations, water lines, and buttocks are drawn together in the lines drawing. This figure shows one of the possible arrangements, probably the most common one, as stations and water lines are symmetric for almost all ships. It is sufficient to draw only a half of each one. Let us take a look to the right of our drawing. We see the set of stations represented together in the body plane. The left half of the body plan contains stations 0 to 4, that is the stations of the afterbody, while the right half is composed of stations 5 to 10, that is the forebody. The set of buttocks known as shear plan is placed at the left of the body plan. Beneath is the set of water lines. Looking with more attention to the lines drawings, we find out that each line appears as curved in one projection and as straight lines in the other two. For example, stations appear as curved lines in the body plan, however as straight lines in the shear and in the water lines plans. The station segments having the highest curvature are those in the bilge region, that is between the bottom and the ship side. Often no buttock or water lines cuts them. The water line where the fully loaded ship is intended to float is called a design water line. Normally is shown by DWL. The curves of plans shown above are best represented using parametric spline curves, by which the curves are defined by a parameter S rather than directly by X and Y coordinates. The parameter S is defined as the cumulative length of segments of the line from the start point up to the point in question. Note that the spline in terms of X, Y coordinates is expressed by the differential equation of the deflection of a simple beam, which may become unrealistic when the slope y prime of the line being represented becomes so large that it cannot be assumed equal to 0. To construct the ship lines, one must make sure that the following continuities exist between each segment of the lines: geometric continuity, also function continuity, slope continuity, the first derivative, and also curvature continuity, referred to as second derivative. Sectional area curve. The sectional area curve is shown here as an example for a ship with parallel middle body. This curve represents the longitudinal distribution of cross-sectional area below the design waterline. Therefore, the area under this curve is the volume of the water displaced by the vessel up to the design waterline, or volume of displacement. Note that displacement refers to the mass of the displaced liquid. It is possible to present the curve in a dimensionless form by dividing the vertical axis by the midship area and the horizontal axis by the ship length. Note that the center of this curve is equal to the longitudinal center of buoyancy of the vessel. Table of offsets. In shipyard practice, it has been usual to derive from the lines plan a digital description of the hull known as table of offsets, as shown in this table. The table of offsets contains half breadth measured at the stations and on the water lines appearing in the lines plan. The result is a table with two entries in which the offsets, half breadth, are grouped into columns, each column corresponding to a station, and in rows, each row corresponding to a water line. Coefficients of form. In ship design, it is often necessary to clarify the hulls and to find relationships between forms and their properties, especially the hydrodynamic properties. The coefficients of form are the most important means of achieving this. By their definition, the coefficients of form are non-dimensional numbers. The block coefficient is the ratio of the molded displacement volume, nabla, to the volume of the rectangular block with the dimensions L, B, and T as shown in this figure. Note that the molded displacement and generally molded ship dimensions are those where the shell plating of the ship is not considered. In other words, the inside dimensions are called the molded dimensions. The L here in this equation can be the length between perpendiculars or the length of waterline. Values of CB at design displacement may vary from about 0.3 0.36 for a fine high-speed vessel to about 0.92 for a slow bulk carrier. The midship coefficient Cm is defined as the ratio of the midship section area Am, as we can see here in this figure, to the product of the breadth and the draft Bt. The prismatic coefficient Cp is the ratio of the molded displacement volume nabla to the product of the midship section area Am and the length L. This figure shows a distribution of sectional area for two prismatic coefficients. The difference between the two curves stems from the fact that the ship with smaller Cp will have the larger Am. The vessel with a low value of Cp or Cb is said to have a fine hull form, while one with a high value of Cp has a full hull form. Let us now note the water plane area by AW. Then we define the water plane area coefficient by this equation. The vertical prismatic coefficient can also be defined as we can see here in this equation. Note that it is possible to change the length or draft of a vessel without changing the dimensionless coefficient presented here. Wetted surface. For a vessel floating at a given waterline, the total area of its outer surface in contact with the surrounding water is known as the wetted surface. The knowledge about the wetted surface is important for the estimation of the frictional resistance to the motions of a vessel. The wetted surface is customarily calculated for a vessel at several waterlines and appears as one of the curves of form or hydrostatic curves. The wetted surface of a shell plating is virtually that of the molded form. Therefore, calculations of the molded surface of a hull plus that of the appendages extending beyond the shell may be considered as the entire wetted surface. Wetted surface coefficient. In order to compare the wetted surface of different ships, it is useful to calculate a dimensionless coefficient which relates the wetted surface to the basic characteristics of the hull. Such a coefficient is shown by CWS, as we can see here. Here, WS is the wetted surface up to any waterline. For normal ships, CWS ranges from 2.6 to 2.9. It can be shown that CWS is mainly a function of beam to draft ratio and Cm midship coefficient. Capacity. The dead weight of a ship is the difference between the full load displacement weight and the light ship weight. The latter is the weight of hull steel, machinery, weight, and outfit. The actual payload or cargo dead weight is obtained by deducing the typical maximum values of the variable weights of fuel, stores, fresh water, water ballast, crew, and other effects from the total dead weight. Basic ship hydrostatics. To develop the basic concepts of ship stability, it is assumed that 1. The water is incompressible. 2. Viscosity plays no role. 3. Surface tension plays no role. 4. The water surface is plane. The first assumption is practically exact in the range of water depth we are interested in. The second assumption is exact in static conditions, that is without motion, and a good approximation at the very slow rates of motion discussed in ship hydrostatics. The third assumption is true for the sizes of floating bodies and the wave heights we are dealing with. The fourth assumption is never true, not even in the sheltered waters of a harbor. However, this hypothesis allows us to derive very useful general results and calculate essential properties of ships and other floating bodies. Archimedes' principle. A body immersed in a fluid is subjected to an upward force equal to the weight of the fluid displaced. The above statement is known as Archimedes' principle. This force, which is referred to as buoyancy force, is applied in the center of the displaced volume, submerged volume. The Archimedes principle can be demonstrated for a general submerged body as shown in this figure. Let the surface of the body be S, and let P be the horizontal plane that cuts in S the largest contour as shown here. The plane P divides the surface S into two surfaces, S1 situated above P and S2 under P. We assume that S1 is defined by Z equals F1 as a function of XY and S2 by this equation. The hydrostatic force on an element dA of S1 is P times dA. As we can see here, note that pressure at a point is the same in all directions, and this statement is known as Pascal's principle. This force is directed along the normal N to S1 in the element of area. If the cosine of the angle between N and the vertical axis is cosine of N and Z, the vertical component of the pressure force on dA equals this equation, as the cosine times dA is the projection of dA on a horizontal plane, that is dx times dy. We conclude that the vertical hydrostatic force on S1 is equal to this equation. Let us consider now an element of S2 opposed to the one we considered on S1. We reason as above, taking care to change signs. We conclude that the hydrostatic force on S2 is obtained using this equation. Then the total force on S is given by this integral equation. The integral in this equation in fact yields the volume of the submerged body. Thus F equals to the weight of the liquid displaced by the submerged body. It remains to show that the horizontal components of the resultant of hydrostatic pressures are equal to 0. This can be predicted by intuition. In fact, if the resultant of the horizontal components would not be 0, we would obtain a free propulsion force. The conditions of equilibrium of a floating body. A body is said to be in equilibrium if it is not subjected to accelerations. Newton's second law shows that this happens if the sum of all forces acting on that body is 0, and the sum of the moments of those forces is also 0. Two forces always act on a floating body: the weight of that body and the buoyancy force. In this section, we show that the first condition for equilibrium, that is the one regarding the sum of forces, is expressed as Archimedes' principle. The second condition regarding the sum of moments is stated as Stevens' law. Stable equilibrium. If the floating body initially at equilibrium is disturbed by an external moment, there will be a change in its angular attitude. If upon removal of the external moment, the body returns to its original position, it is said to have been in stable equilibrium and to have positive stability. An example of stable equilibrium is shown here for a watertight body having a rectangular section with dimensions and center of gravity illustrated here. Assume that it will float with half its volume submerged, as shown in these figures. It can come to rest in either of two positions, A or C. In either of these positions, the center of gravity and center of buoyancy are in the same vertical line. Also, as the body is inclined from A to B or from C to D, a moment is developed which tends to rotate the body back to its original position, and the same situation would exist if it were inclined in the opposite direction. If the 20 centimeter dimension as shown here were reduced with the center of gravity still on the center line and 2.5 centimeters below the top, a situation would be reached where the center of buoyancy would no longer move far enough to be at the right of the center of gravity as the body is inclined from A to B. Then the body could come to rest only in position C, neutral equilibrium. If, on the other hand, a floating body that assumes a displaced inclination because of an external moment remains in that displaced position when the external moment is removed, the body is said to have been in neutral equilibrium and has neutral stability. An example of neutral equilibrium is a body of revolution with its center of gravity exactly on the axis of revolution as illustrated here. When such an object is rotated to any angle, no moment is produced since the center of buoyancy is always directly below the center of gravity. It will remain at any angle it is placed. Note that it is worthy to mention a main difference between a submerged and floating body is exactly this, okay? The center of buoyancy in a submerged body is fixed, while in a floating body the center of buoyancy generally shifts as the body rotates. Unstable equilibrium. If a floating body displaced from its original angular attitude by an external force continues to move in the same direction after the force is removed, it is said to have been in unstable equilibrium and was initially unstable. Forces. Let us assume that a body floats freely, then the weight of that body and the hydrostatic forces acting on it are in equilibrium. Archimedes' principle can be reformulated as here. The weight of the volume of water displaced by a floating body is equal to the weight of that body. The weight of the fluid displaced by a floating body is appropriately called displacement. We denote the displacement by the uppercase Greek letter delta, as we can see here. If the weight of the floating body is W, then we can express the equilibrium of forces acting on the floating body by this equation. For the volume of the displaced liquid, we use the symbol nabla. In terms of the above symbols, Archimedes' principle is this equation. This equation can be written as we can see here, okay, where Wi is the weight of the ith item in the floating body. Also, gamma here is in fact the specific weight of the fluid. From this equation, it is possible to compute the draft of the floating body. Note that this equation can be written in terms of mass as we can see here. Moments. Here we discuss the second condition of equilibrium of a floating body. The sum of the moments of all forces acting on it must be zero. This condition is fulfilled in this figure where the center of gravity and the center of buoyancy B of the floating body are on the same vertical line. The weight of the body and the buoyancy force are equal, opposed, and act along the same line. The sum of their moments about any reference is zero. Let us assume that the center of gravity moves in the same plane to a new position G1 as shown in this figure. The sum of the moments is no longer zero. It causes a clockwise inclination of the body by an angle phi. A volume submerges at right, another volume emerges at left. The result is that the center of buoyancy moves to the right to a new point that we mark by B phi. The floating body will find a position of equilibrium when the 2 points G1 and B phi are on the same vertical line. This situation is shown here in this figure. There is a possibility of redrawing this figure so that all situations are shown in one figure. To do this, instead of showing the body inclined clockwise by an angle phi and keeping the waterline constant, we keep the position of the body constant and draw the waterline inclined counterclockwise by the angle phi. Thus, in this figure, the waterline corresponding to the initial position is W0, L0. The weight force acts through the initial center of gravity G0. It is vertical, that is perpendicular to the waterline W0, L0. The buoyancy force, also equal to the weight force, acts through the initial center of buoyancy B0. It is vertical, that is perpendicular to the initial waterline. We assume now that the center of gravity moves to a new position, G1. The floating body rotates in the same direction by an angle phi until it reaches a position of equilibrium in which the new waterline is W phi, L phi. The new center of buoyancy is B phi. The line connecting G1 and B phi is vertical, that is perpendicular to the waterline W phi, L phi. The weight and the buoyancy force act along this line. Thus, in the case of a floating body, the second condition of equilibrium is satisfied if the center of gravity and the center of buoyancy are on the same vertical line. This condition is attributed to the Simon-Stevin. Note that contrary to a submerged submarine, where the center of buoyancy does not move with respect to the motions of the submarine, the center of buoyancy of a ship or surfaced submarine shifts with respect to the ship motion as the ship is inclined. Therefore, the moment acting on a surface ship can change from a riding moment to a heeling moment, or vice versa, as the ship is inclined. But this cannot occur on a submerged submarine unless there is a shift of the ship's center of gravity. A definition of stability. When a body floats freely but is completely submerged, its weight equals exactly its volume multiplied by the specific gravity of the liquid. This body is in neutral equilibrium because it can float at any depth. Any small perturbation will move the body from a depth to another one. If the weight of the body is larger than its total volume multiplied by the specific gravity of the liquid, then the body will sink. Summing up, we may distinguish three cases. First, the total volume of a body is larger than its weight divided by the specific gravity of the water. The body floats in this condition at the surface, and we can control the draft by adding or reducing weights. The second condition, the weight of the body is exactly equal to the total volume multiplied by the specific gravity of the liquid. The body can float at any depth, and we cannot control the position by adding or reducing weights. Any additional weight would cause the body to sink, bringing it into case 3. Reducing even slightly its weight will cause the body to come to the surface. Its situation changes to case 1. The third condition, the weight of the body is larger than its volume multiplied by the specific gravity of the water. The body will definitely sink. To change its position, we must either reduce the weight until we reach at least situation 2 or add buoyancy in some way. In the above analysis, we assume that the specific gravity of the liquid, gamma, is constant throughout the liquid volume. This assumption may not be correct if large variations in temperature or salinity are present, or if the liquid volume consists of layers of different liquids. Interesting situations can arise in such cases. Other situations can arise at large depths at which the water density increases while the volume of the floating body shrinks because of the compressibility of its structure. Effect of density of medium. A decrease in the fluid density where a vessel floats requires an increase in the displacement volume, nabla, to satisfy the static equilibrium requirements. For instance, a ship moving from salt water to fresh water experiences an increase in draft delta T. This increase can be calculated by equating the increase in displacement volume to the volume of a layer of buoyancy of uniform thickness delta T distributed over the original load water plane. The increase in displacement volume can be obtained using this equation. Here, subscript S refers to salt water and F refers to fresh water. Based on the assumption that ship is wall-sided, the equal layer of buoyancy is obtained using this equation. Here, AWP is the water plane area. Therefore, one can write the following equation to obtain the changes in the draft. The centroid of the underwater body may shift both vertically and longitudinally with such a change in medium. In particular, an increase in draft as a result of a decrease in fluid density causes the vertical location of the center of buoyancy to rise with respect to the keel as a result of the increase in displacement volume nabla. Initial stability. This figure is a vertical transverse section through a ship in upright condition that is unheeled. A ship or submarine is designed to float in the upright position. If this section passes through the center of buoyancy B, we know from Stevens' law that it contains the center of gravity G. The water line is W0, L0. The weight force W acts through the center of gravity G, the buoyancy force nabla through the center of buoyancy B, 0. The forces W and delta are equal and collinear, and the ship is in an equilibrium condition. Let the ship heel to the starboard with an angle phi. We assume that the heel angle is small. As previously explained, we leave the ship as she is and draw the water line as inclined to port with the same angle phi. This is done in this figure where the new water line is W phi L phi. If the weights are fixed as they should be, the center of gravity remains in the same position G. Because the volume submerges at starboard and an equal volume emerges at port, the center of buoyancy moves to starboard to a new position B phi. Both forces W and del are vertical, that is perpendicular to the water line W phi L phi. These two forces form a moment that tends to return the ship toward port, that is to her initial condition. We say that the ship is stable. This figure here also shows the ship heeled toward starboard with an angle phi. In this situation, the moment of the two forces W and del heels the ship further towards starboard. We say that the ship is unstable. The difference between the situations in these figures can be described elegantly by the concept of metacenter. For a ship, the dot point line is the trace of the port to starboard symmetry, that is the center line. More generally, for any floating body, the dot point line is the line of action of the buoyancy force before heeling. The new line of action of the buoyancy force passes through the new center of buoyancy and is perpendicular to W phi L phi. The two lines intersect in the point M phi. This point is called metacenter. For a specific ship, the location of this point will vary with ship's displacement and trim or heel. But for any given draft, it will always be in the same plane. We can see now the difference between the two heeled situations shown in this figure. In B, the metacenter, in this figure, the metacenter is situated above the center of gravity G. However, in C, in this figure, the metacenter is situated below the center of gravity G. We conclude that the equilibrium of the floating body is stable if the metacenter is situated above the center of gravity. It must be emphasized here that the definition of the metacenter is not connected at all with the form of a ship. Therefore, the fact that in the above figures the metacenter is the intersection of the new line of action of the buoyancy force and the central line is true only for symmetrical hulls healed from the upright condition, unless there's an abrupt change in the shape of the ship in the vicinity of the waterline. Point M will remain practically stationary with respect to the ship as it is inclined to small angles up to about 7 or sometimes 10 degrees. For a general floating body, we can reformulate the definition as follows. Let us consider a floating body and its center of buoyancy be phi. Let the line of action of the buoyancy force be r. If the body changes its inclination by an angle delta phi, the center of buoyancy changes its position to b phi plus delta phi, and the new line of action of the buoyancy force will be, say, p. When delta phi tends to 0, the intersection of the lines r and p tends to a same point, which is called metacenter. Thus, the metacenter is the center of curvature of the curve of centers of buoyancy, metacentric height. In the preceding section, we learned that a surface ship is initially stable if its initial metacenter is above the center of gravity. For actual calculations, we must find a convenient mathematical formulation. We choose a reference point K at the intersection of the center line and the ship baseline, and we measure vertical coordinates from it upwards. Thus define K is the origin of Z coordinates. A good recommendation is to choose K as the lowest point of the ship keel. Then there will be no negative Z coordinates. In the same figure, M is the initial metacenter, that is the metacenter corresponding to the upright condition. We can write this equation: Gm equals Kb plus Bm minus Kg, and the condition of initial stability is expressed as Gm greater than 0. The vector Gm is called metacentric height. The vector Kb is the z coordinates of the center of buoyancy. It is calculated as the z coordinate of the centroid of the submerged hull as one of the results of hydrostatic calculations. The vector Bm is the metacentric radius. The vector Kg is the z coordinate of the center of gravity of the floating body. It results from weight calculations. The quantities Kb and Bm depend upon the ship geometry. The quantity Kg upon the distribution of masses. A lemma on moving volumes or masses. This figure shows a system of two masses, m1 and m2. Let the x coordinate of the mass m1 be x1, that of the mass m2 x2. The center of gravity of the system is g, and its x coordinate is given by this equation. Let us move the mass m2 a distance d in the x direction. The new center of gravity is g asterisk, and its x coordinate is calculated using this equation. The product dm2 is the change of moment caused by the translation of the mass m2. The center of gravity of the system moved a distance equal to the change of moment divided by the total mass of the system. A formal statement of this lemma is given here. Given a system of masses, if one of its components is moved in a certain direction, the center of gravity of the system moves in the same direction, a distance equal to the change of moment divided by the total mass. Small angles of inclination. In this section, we proved two very important theorems for bodies that incline at constant displacement. This is the case of floating bodies that change their inclination without the addition or loss of weights. constant displacement means constant volume of displacement. A second assumption in this section is that the angle of inclination is small. The results developed under this assumption are valid for any floating body. The results are valid for any angle of inclination only for floating bodies belonging to a particular class of forms called wall-sided. A theorem on the axis of inclination. Let us assume that the initial water plane of the body shown in this figure is W0, L0. Next, we consider the same body inclined by a small angle phi, such that the new water plane is W phi, L phi. The weight of the body does not change. Therefore, also the submerged volume does not change. It can be shown that the axis of inclination passes through the centroid of the water plane area, which is also known as center of flotation. The center of flotation, which is the point in the water plane at which a weight added to a vessel would produce parallel sinkage with no change of trim or heel, is at the centroid of water plane area. The longitudinal location of center of flotation, LCF, is found by calculating the longitudinal moment of water plane area in conjunction with the calculation of area as shown here. Let the initial water plane of a floating body be W0, L0. After an inclination at constant volume of displacement with an angle phi, the new water plane is W phi, L phi. The intersection of the two water planes is the axis of inclination. If the angle of inclination tends to 0, the axis of inclination tends to a straight line passing through the centroid of the water plane area called the center of flotation. In practice, this property holds if the angle of inclination is sufficiently small. For heeling of a vessel, this can mean a few degrees, up to 5 degrees for some forms, even 15 degrees for others. If the inclination is the trimming of an intact vessel, the angles are usually small enough, and this property always holds. The property also holds for larger heel angles if the floating body is wall-sided. This is the name given to floating bodies whose surface includes a cylinder in the broader geometrical sense with generators perpendicular to the initial water plane. Metacentric radius. Let us refer again to this figure. As we shall see, the vector b phi m phi plays an important role in stability. Leaving the subscript phi, we generally call bm metacentric radius. In this section, we calculate its magnitude. To do so, we must find the shift of the center of buoyancy b for a small angle of inclination phi. We use here the lemma on moving volumes. To find the changes in the center of buoyancy due to a small inclination phi, we can use similar equations as those used in the equation for moving masses, as we can see here for xb, yb, and zb. In these equations, y times tangent of phi times dx times dy is the volume of the element as shown in this figure. To make things easier, we have taken the origin of coordinates in the initial center of buoyancy b phi. Measure the x coordinate parallel to the axis of inclination, positive forward, the y coordinate transversely, positive leftward, and the z coordinate vertically, positive upward. The coordinates of the center of buoyancy b phi are obtained by integrating the changes of moment of the elemental volume y times tangent of phi times dx times dy as shown here over the water plane area S. Here I is the moment of inertia of the water plane area about the axis of inclination. Ixy is the product of inertia of the same area about the axis x and y. As we assumed that the angle phi is small, these equations are reduced to these equations. The coordinate z can be neglected totally for small angles of phi, as it is second order. For ships with port to starboard symmetry, the product of inertia is also 0. Therefore, B0, B phi is essentially equal to YB as shown in this figure. Based on this figure, the length of the curve B0, B phi is equal to BM phi. Therefore, we can write the following equation, which can be simplified to this one. Therefore, the magnitude of metacentric radius Bm is equal to the ratio of the water plane moment of inertia about the axis of inclination to the volume of displacement. This metacentric radius is in fact the transverse metacentric radius against the longitudinal one, where the water plane moment of inertia is obtained with respect to transverse axis passing through the longitudinal center of flotation. Note that ZB is always positive. This means that the curve of centers of buoyancy presents its concavity towards the waterline. The curve of centers of buoyancy. This figure shows a floating body inclined by some angle phi. The corresponding waterline is W1, L1, and the center of buoyancy is B1. Let us assume that the inclination increases by an additional small angle phi. Let the new waterline be W2, L2, and the corresponding center of buoyancy B2. For a small angle phi, we can write the coordinates of the new center of buoyancy as shown here. Differentiating these equations gives these equations. Thus, the slope of the tangent to the B curve at B2 is phi. This is the assumed angle of inclination. We reach the important conclusion that the tangent to the B curve in a point B phi is parallel to the waterline corresponding to the center of buoyancy B phi. Metacenters for various axes of inclination. The moment of inertia I is calculated about the axis of inclination. This axis passes through the centroid F, center of flotation of the water plane, and so does any other axis of inclination. It can be shown that there is a pair of orthogonal axes such that the moment of inertia about one of them is minimum and about the other maximum. Then the metacentric radius corresponding to the former axis is minimum and the moment about the latter is maximum. Correspondingly, one of the metacentric radii is minimum and the other maximum. In the theory of moment of inertia, the two axes for which we obtain the extreme values of moment of inertia are called principal axes, and the corresponding moments called principal moments of inertia. When the water plane area has an axis of symmetry, this axis is in fact one of the principal axes. The other one is perpendicular to the first. The water plane area of ships in upright condition has an axis of symmetry. The intersection of the water plane and the centerline plane as shown here. The moment of inertia about this axis is the smallest one. It is used to calculate the transverse metacentric radius. The moment of inertia about the axis perpendicular in F to the center line is the largest as shown here. It enters in the calculation of the longitudinal metacentric radius. To give an idea of the relative orders of magnitude of the transverse and longitudinal metacentric radii, let us consider a rectangular form barge whose length is L, breadth B, and draft T as shown here. The volume of displacement equals nabla equals L BT. The transverse metacentric radius results from this equation, and the longitudinal metacentric radius is calculated using this equation. So the ratio of the two metacentric radii is obtained using this equation. This is the main reason why the ships are more stable longitudinally than transversely. Thus, if the ship's center of gravity were to rise vertically, the ship would capsize transversely long before there would be any danger of capsizing longitudinally. Note that for a totally submerged submarine, there is no metacentric radius. Thus, the longitudinal and transverse stability are equal. In this case, the center of buoyancy is the metacenter. Note that in case of submarines, to guarantee the stability, the center of gravity must be lower than the center of buoyancy. In case of a submarine, the riding arm is calculated using this equation. Therefore, the maximum value of the riding arm occurs at 90 degrees. The most critical period for submarine transverse stability is during submerging or surfacing, because of the effect of the free liquids in the main ballast tanks, which are going to be addressed later in this video. Tons per centimeter immersion, shown also by TP centimeter, and moment to trim 1 centimeter MT centimeter. Note that it is possible to calculate the changes in displacement resulting from small changes in a vessel draft using this equation. It is possible to define a quantity called tons per centimeter immersion, TP centimeter, as we can see here. This happened because the freshwater density is 1 ton per cubic meters. Now let's calculate the moment necessary in order to change the trim of a ship with the length between perpendiculars of LPP by 1 meters, which is also referred to as MT meter or MT centimeter, in case the moment necessary to change the trim by 1 centimeter. The corresponding trim angle can be computed using this equation. Now let's calculate the moment necessary in order to change the trim of a ship with the length between the perpendiculars of LPP by 1 meter, which is also referred to as MTM or MTCM, in case the moment necessary to change the trim by 1 centimeter. Corresponding trim angle can be computed as we can see here. Note that the displacement and buoyancy are separated by a distance of GZL equals GML times sine of phi, where GML is the longitudinal metacentric height, as we can see here its definition. Both the displacement and buoyancy form the following moment. Therefore, to trim the vessel, the moment must be at least equal to this expression. For small angles of trim, the sine is equal to tangent, and one can reach to the following result. Here, MTM is the moment that one needs to apply to trim the vessel by 1 meter. Note that this moment, as it is directly proportional to a vessel displacement, it is also proportional to water density. Therefore, at any draft, this moment increases when in salt water compared to its value in fresh water. Moment to trim 1 centimeter is calculated as we can see here. Note that sometimes it is acceptable to assume that GML equals to BML. This assumption is true when the vertical center of gravity coincides almost with the center of buoyancy. Therefore, using this assumption, MT centimeter is as follows. Another important point is the importance of distinguishing Km from GM, where Km in fact is the height of metacenter, and it is a purely geometrical quantity, while GM is the metacentric height, which involves the location of ship's center of gravity. It is also possible to calculate the moment that is necessary to heal a ship 1 degree. This moment can be calculated as we can see here. Thus, within the range of inclinations where the metacenter is stationary, the change in the angle of heel produced by a given external moment can be found by dividing the moment by the moment to heel 1 degree. Longitudinal center of buoyancy. The usual method to estimate displacement is to calculate sectional areas of a vessel along its length and then integrate them longitudinally. The LCB, longitudinal center of buoyancy, is also calculated in the same way for the considered waterline. This figure shows an example of sectional area curve of a vessel with a 5 meters waterline. One can identify the LCB in this figure. Note that it is also possible to calculate the displacement through a vertical integration of waterplane areas at several waterlines. Vertical center of buoyancy by vertical integration of waterplanes. Vertical center of buoyancy, which is also called KB, is calculated by dividing the vertical moment of the volume of displacement above the baseline at any waterline to its displacement, which mathematically is shown as follows. The calculation requires a curve of waterplane area with respect to draft as shown in this figure. Vertical center of buoyancy by integration of displacement curve. Another method of obtaining KB depends upon the fact that the curve of volume of displacement versus draft is the integration of the curve of waterplane areas. This figure shows a curve of volume of displacement against draft. Therefore, the area between the curve and the horizontal axis, i.e. displacement, gives this equation. After calculating this moment, the KB is obtained using this equation. Approximate formulas for vertical center of buoyancy. In the initial stages of design, the height of the center of buoyancy KB may be required, yet a displacement curve is not available, precluding a calculation of KB using the methods just presented. Therefore, approximate formulas may be used for this purpose. For instance, the Moorish formula, also known as Norman's formula, gives this expression. T here is the molded mean draft. Nabla is the corresponding volume of displacement, and AWP is the corresponding waterplane area, all in a consistent system of units. The formula is shown to give good results for vessels with ordinary forms. Numerical integration in naval architecture. 3 methods for numerical integration are described here: the trapezoidal and Simpson's first and second rules. Many naval architectural problems require the calculation of the definite integral as shown here. The function f is bounded in the finite interval a and b. We approximate the definite integral by the weighted sum of a set of function values fx1, fx2, up to fxn, evaluated or measured at endpoints between a and b as shown here in this equation. In naval architecture, the coefficients ai are called multipliers. In some books on numerical methods, they are called weights. The numerical solutions that are addressed here are based on geometric reasoning, considering integral of fx from a to b as the area under the curve expressed by fx between x equals a and x equals b. For instance, consider this curve. The area under this curve can be approximated using this equation. The first moment of this area about the OY axis is given using this equation. Thus, the distance of the centroid of this surface to the y-axis is computed using this equation. The first moment with respect to the OX axis is calculated again using a similar equation as shown here. Thus, using the same procedure as before, the distance of the centroid of this surface to the x-axis is calculated using this equation. Using a similar method, we can write the second moment or moment of inertia as follows. The trapezoidal rule. Consider the function fx with known values of fx1, fx2, fx3, fx4, and fx5 as shown here. Then the integral here of the function, which represents the area under the curve fx between x1 and x5. The area shown in this figure can be approximated as the sum of 4 trapezoidal areas, which are obtained by connecting fx1, fx2, fx3, fx4, and fx5 by straight line segments, the dashed dotted line as we can see here, as shown here in this figure. So here we can see the equation obtained using trapezoidal method. The difference between x2, x1, and x3 and x2 and etc. can be assumed to be a constant value h for constant x spacing. Okay, therefore the integral equation can be reduced to a simpler form as we can see here. Note that the error is proportional to the square of h, since the original function is being approximated as a linear function. Thus, if we have the subinterval, the error is reduced approximately in the ratio 1/4. Simpson's first rule. This time, to compute the integral of the function fx between x equals a and x equals e, as shown in this figure and this equation, the function here fx is approximated as a second order parabola or polynomial of degree 2, as we can see here. This parabola is shown in this figure by the dashed dotted line. It can be shown that based on Simpson's first rule, the area A, B, C, D, E, A can be computed using this equation. For an arbitrary number of subintervals, the Simpson's first rule is written as follows. Note that the application of the Simpson's first rule requires that the number of subintervals to be an even number. Thus, the values of a function fx will be available at an odd number of points. Note that in this case the error is proportional to h to the power of 4, and so if we have the subinterval, the error is reduced approximately in the ratio 1 divided by 16. Simpson's second rule. In this case, the function fx is approximated as a third order parabola or polynomial of degree 3 as follows. For an arbitrary number of subintervals, the Simpson's first rule is written as shown here. Half-space ordinates. Near the ends of a ship, it is customary to introduce additional body plans. This is done to better define the hull form in these regions, as it is changing more rapidly compared to the midship region. In this case, in order to accommodate this combination of spacings, the Simpson's first rule multipliers, for instance, are reduced to 1/2 their normal values as shown in this figure. Hydrostatic curves. There are no universally accepted standards for plotting hydrostatic data, and we can find a wide variety of styles. The curves are plotted a function of the draft T at constant trim and heel. In general, the trim equals 0, ship on even keel condition, but it is possible to plot hydrostatic curves for any given non-zero trim. The heel is almost always 0. The hydrostatic curves represent data calculated for parallel water planes. Let us refer to this figure. The draft axis is vertical, positive upward. The various properties are measured horizontally, each at its own scale, so that all curves can be contained in the same paper format. In our example, the curves of volume of displacement, nabla, displacement in fresh water, delta FW, displacement in salt water, delta SW, water plane area, AW, a moment to change trim by 1 meter, MCT, and longitudinal metacenter above Q, KM, are measured along the lower scale, that is to be read as 0 to 100 cubic meter, square meter, meter to the power of 4 divided by meter, or meters, respectively. The vertical center of buoyancy, KB, the transverse metacenter above Q, KM, the longitudinal center of flotation, LCF, and the longitudinal center of buoyancy, LCB, are measured along the upper scale, graduated from -2 to 5 meters. To simplify things, we plot the coefficients of form CB, CM, CP, and CWL in another graph shown in this figure. Let us return to the volume and displacement values represented in hydrostatic curves. The displacement volume, nabla, is usually the volume of the molded hull. The displacements in fresh and in salt water should be total displacement that include the displacements of shell plates and appendages. Appendages found in all kinds of ships include rudders, propellers, propeller shafts and struts, bilge keels, and roll fins. In a still single screw cargo vessel, the volume of all appendages is usually slightly less than 1% of the molded volume, and the shell plating is by far the largest contributor, perhaps 75%. For very large ships, this percent tends to be lower, less than 0.5%. For a typical large tanker, in multiple screw vessel, the appendages constitute a greater percentage of the molded volume than in the case of single screw vessel. Bungee curves and their use. This figure shows the midship section of a ship in solid, thick line. The bungee curves give the sectional area as well as the moment of the sectional area about the baseline, as shown in this figure. The following figure shows a typical transverse section through a ship on one side of the center line, such as a body plant station. The area KCL1W1K from the baseline up to waterline W1L1 may be obtained by one of the rules of integration. Twice the area plotted to a convenient scale and at the same draft as W1L1 would appear as the point Q in the following figure. Similarly, the area KCLWK from the baseline up to WL could be obtained and would give the point P in this figure. The curve K prime Q P F prime T represents the area of the full section on both sides of the center line from the baseline up to any water line. For wooden vessels, the half section should be taken to the outside of the planking, but for steel vessels, it is customary to draw the curve of areas for sections taken to the molded line. The curves of cross-sectional area for all body plant stations are collectively called bungee curves. One of the principal uses of bungee curves is determining volume of displacement of the ship at any level or trimmed water lines. The bungee curves are especially useful for the calculation of displacement volume and LCB, longitudinal center of buoyancy, where the water line at which the ship is floating is not for the even keel condition. In the case of a trimmed water line, the trim line may be drawn on the profile of the ship and drafts are read at which the bungee curves are to be entered. By drawing a straight line across the ship profiles within bungee curves, as we can see in this figure, the drafts at which curves are to be read appear directly at each section. Therefore, the hydrostatic curves are applicable in the case of even keel conditions, and in the case of significant trim angles, the Barnagine curves are preferable. Statical stability at large angles of heel. Here we are going to discuss the properties of submerged hulls as functions of heel at constant displacement volume. The assumption of constant displacement volume recognizes the fact that while a ship heels or rolls, her weight remains constant. By virtue of Archimedes' principle, constant weight implies constant displacement volume. The central notion here is the riding arm. We shall show how to calculate and represent the riding arm in a set of curves known as cross curves of stability. Another topic is the plot of the riding arm as function of the heel angle for a given displacement volume and a given height of the center of gravity. This plot is called curve of statical stability, and it is used to assess the ship's stability. The riding arm. In this figure, we consider a ship whose waterline in upright condition is W0, L0. The corresponding center of buoyancy is B0 and the center of gravity G. Let us assume that the ship heels to starboard by an angle phi. The new waterline is W phi, L phi, and the center of buoyancy moves towards the submerged side to the new position B phi. The weight force equals to delta, passes through G and is vertical, that is perpendicular to W phi L phi. The buoyancy force also equal to delta, passes through B phi and is also perpendicular to W phi L phi. The perpendicular from G to the line of action of the buoyancy force intersects the ladder line in Z. The forces of weight and buoyancy produce a riding moment whose value is as shown in this equation, delta times gz. Note that the riding moment exists at any inclination angle where the forces of weight and buoyancy act to move the ship toward the upright position, a situation demonstrated in this figure. As the displacement is a constant for all angles of heel, we can say that the riding moment is characterized by the riding arm gz. Based on this figure, we can write this equation. The distance Lk is called the value of stability cross curves. This quantity results from hydrostatic calculations based on the ship lines. It is important to note that Lk is measured here from K, a point preferably chosen as the lowest keel point or the projection of the lowest keel point on the midship section. The resulting Lk value is thus always positive. The relationship between the value of the stability cross curves Lk and the heel angle phi is not linear and in general cannot be defined explicitly. For small angles of heel, a linear expression for the riding arm gz can be derived from the following equation and using this figure. But what do we mean by small angle? The answer is given by the same figure. This equation holds true as long as the metacenter M does not move visibly from its initial position. Thus, for many ships, an angle equal to 5 degrees is small, while for a few others, even 15 degrees may be a small angle. The value depends on both ship forms and loading condition. A useful way of plotting the Lk values is shown in this figure. Here, the Lk curves are plotted as functions of the displacement volume nabla for a set of constant heel angle values. Thus, we have a curve for phi equals 10 degrees, one for phi equals 20 degrees, and so on. To use this equation for a given displacement volume, say nabla 0, it is necessary to draw a vertical line v equals nabla 0 and read the values where this line crosses the curves. Hence the term cross curves of stability. The curve of statical stability. The plot of the riding arm gz calculated from this equation as function of the heel angle phi at constant nabla and kg values is called curve of statical stability. Such diagrams are used to evaluate the stability of the ship in a given loading condition. For a full appreciation, it is necessary to compare the riding arm with the various heeling arms that can endanger stability. An example of statical stability curve is shown in this figure. Let us identify some properties of the riding arm curves. One important value is the maximum GZ and the heel angle where this value occurs. For example, in this figure, the maximum riding arm value is 1.009 meters and the corresponding heel angle is 50 degrees. Another important point is where the GZ curve crosses 0. The corresponding phi value is called angle of vanishing stability. In our example, the riding arm curve crosses 0 at an angle greater than 90 degrees in a region outside the plot frame. The angle of vanishing stability can often occur at less than 90 degrees. A very useful property refers to the tangent in the origin of the riding arm curve. The slope of this tangent at phi equals 0 is given by this equation. In the curve of statical stability at the heel angle 1 radian, approximately 57.3 degrees, draw a vertical and measure on it a length equal to that of GM. Draw a line from the origin of coordinates to the end of the measured segment. This line is tangent to the GZ curve. From the tangent formed by the heel angle axis, the vertical at 1 radian, and the tangent in origin, we find the slope of the lines as above. It is equal to GM. The tangent in the origin of the riding arm curve should always appear in the curve of statical stability. It gives an immediate visual indication of the GM magnitude and it is a check of the correctness of the curve. This figure also lets us give another appreciation of what small angle means. We can consider as a small those heel angles for which the curve of the riding arm can be confounded with the tangent in its origin. In our example, this holds true for angles up to 7 to 8 degrees. As shown in this figure, the stability curve usually rises above the GZ equals GM times sine phi line at first as inclination angle increases. This is due to an upward and lateral shift of buoyancy at large angles of inclination. This shift produces a significant increase in the riding arm GZ until the deck edge is reached. It can be shown that for a wall-sided ship, as shown here schematically, up to the angle at which the deck edge enters the water, GZ is calculated using this equation. Note that the second part of the above equation emanates from the displacement of center of buoyancy in the z direction, which has been assumed negligible up to here for small angles of heel. Note that the direction of curvature of the statical stability curve near the origin determines whether the ship will develop positive riding arms when the metacentric height is reduced to 0 or becomes slightly negative. For instance, two statical stability curves are shown in these figures for two ships having the same metacentric height but different forms. In figure A, the curve is concave upward, while in figure B, it is concave downward. Assume that the center of gravity of each ship is shifted upward the same distance so that the metacentric height in each case becomes slightly negative. At any angle, the riding arm will be reduced by the same amount in each case, the reduction being the product of the vertical movement of the center of gravity shown here by delta kg and the sine of the angle of inclination. There is an important difference between the resulting statical stability curves. In case A, the ship will heel to a small angle beyond which there will be some positive riding arm, while in case B, the ship will capsize. Note that it is not practical in general to calculate the actual riding arm for all conditions of loading, since the location of center of gravity varies with the ship loading. Waves may have a significant effect on static stability, particularly falling or overtaking waves of approximately the ship length. Riding curves can be drawn by superposing offsets from the wave profile on the body plan used for the calculation of cross curves, and this figure shows typical riding arm curves for a ship in regular waves of the same length as the ship with either wave crest or wave trough amidships. This figure shows typical riding arm curves for a ship in regular waves of the same length as the ship length with either wave crest or wave trough amidships. Effect of beam on statical stability. This figure shows in solid lines a typical ship section and another section in broken lines which differs from the other by an increase in beam. Increasing the beam, as shown in this figure, will at any angle of inclination cause the ship to rise, so that the lost displacement of the shaded volume between the two water lines is equal to the added displacement of the shaded volumes port and starboard between the two shell lines, less the addition of weight involved in increasing the beam. If W1 is the lost displacement between the water lines, W2 the added displacement on the high side, and W3 the added displacement on the low side, with their centroids located at distances A, B, and C from a vertical through the original inclined center of buoyancy B1, the horizontal shift of the center of buoyancy toward the low side D would be found. The riding arm is increased by the amount D due to the shifting of the center of buoyancy. The riding arm would be affected also by any movement of the ship's center of gravity caused by the added weight. As a practical matter, the weight change would probably be small and not far from the ship's center of gravity, and the effect of the weight change on the riding arm would be small, if not negligible. Metacentric height and therefore the riding moments at small angles of inclination are increased by increasing beam because of the large increase in the moment of inertia of the water plane, along with small changes in volume of displacement and vertical positions of the centers of buoyancy and gravity. Effect of depth on statical stability. This figure shows a ship section in solid lines with another in broken lines, which differs by an increase in depth. Weight changes caused by an increase in depth will have a more pronounced effect on statical stability than those associated with a change in beam. This is due to the fact that increasing depth results not only in adding a structure such as shell, framing, and bulkheads between the two positions of the deck at some distance above the ship's center of gravity, but also in raising the entire superstructure and all items installed above the deck through a distance equal to the increase in depths, but also in raising the entire superstructure and all items installed above the deck through a distance equal to the increase in depths. Increasing depth causes the center of buoyancy to shift toward the low side owing to addition of displacement of the shaded volume between the two positions of the deck and the loss of the displacement of the shaded volume between the two water lines. Increasing depth will not result in an increase in riding arm due to shifting of the center of buoyancy until an angle is reached at which the original deck is submerged. Beyond this angle, substantial increase in riding arm may be obtained, particularly if the original freeboard was relatively low. At all angles, riding arms will be decreased because of the upward shift of the center of gravity caused by the added weight and raising of the superstructure and other topside items. Thus, the net effect of increasing depth on riding arm is a decrease until the original deck edge is immersed, and a significant increase above this angle, assuming the beneficial buoyancy effect is greater than the adverse effect of the rise in center of gravity. Therefore, depth should not be increased for the purpose of improving stability unless some decrease in riding arms at the smaller angles of heel can be accepted, or the rise of center of gravity is offset by some measure, such as adding low weight or increasing beam. Effect of other changes in form on statical stability. Chamber home or flare above the waterline in the upright position, as illustrated in this figure, have effects on stability quite similar to a change in beam, except that the major effect on riding arm will be delayed until larger angles of heel are reached. Riding arms at the larger angles are increased by flare and decreased by chamber home. Flare and chamber home have no effect on metacentric height except for a small change in the height of the ship's center of gravity caused by differences in structure. Simple models of stability. When the ship heels at constant displacement, it is sufficient to consider the riding arm as an indicator of stability. Then, to assess the ship's stability, it is necessary to compare the riding arm with the heeling arm. We note the heeling arm by the letter L and indicate the nature of the heeling arm by a subscript. To obtain a generic heeling arm LG corresponding to a heeling moment mg, we divide that moment by the ship weight as shown in this equation. In this figure, we superimposed the curve of a generic heeling arm LG over the curve of the riding arm GZ. For almost all positive heeling angles shown in the plot, the riding arm is positive. We define the riding arm as positive if when the ship is heeled to starboard, the riding moment tends to return it toward port. In the same figure, the heeling arm is also positive, meaning that the corresponding heeling moment tends to incline the ship toward starboard. What happens if the ship heels in the other direction, i.e. with the port side down? Let us extend the curve of statical stability by including negative heel angles as in this figure. The riding arms corresponding to negative heel angles are negative. For a ship heeled towards port, the riding moment tends indeed to return the vessel towards starboard. Therefore, it has another sign than in the region of positive heel angle. The heeling moment, however, in general tends to heel the ship in the same direction as when the starboard is down, and therefore it is positive. Summarizing, the riding arm curve is symmetric about the origin, while the heeling arm curves are symmetrical about the lever arm axis. We can appreciate the stability of a vessel by comparing the riding arm with the heeling arm as long as the heeling moment is applied gradually and inertia forces and moments can be neglected. When the heeling moment appears suddenly, as caused for example by a gust of wind, one has to compare the heeling energy with the work done by the riding moment. Such situations are discussed in this video on the section of dynamic stability. Angles of statical equilibrium. This figure shows the curve of a heeling arm LG superimposed on the curve of the riding arm GZ. In general, those curves intersect at 2 points. They are noted here as phi st1 and phi st2. Both points correspond to positions of statical equilibrium because at both points the riding arm and the heeling arm are equal, and therefore the riding moment and the heeling moment are also equal. Only the first point corresponds to a position of stable equilibrium, while the second point corresponds to a situation of unstable equilibrium. Here we give an intuitive proof of this statement. Let us first consider the equilibrium in the first static point, in the first static angle, phi st1, and assume that some perturbation causes the ship to heel further to starboard by a small angle delta phi. When the perturbation ceases at the angle phi st1 plus delta phi, the riding arm is larger than the heeling arm, returning thus the ship toward its initial position at the angle phi st1. Conversely, if the perturbation causes the ship to heel toward port to an angle phi st1 minus delta phi, when the perturbation ceases, the riding arm is smaller than the heeling arm, so that the ship returns toward the initial position phi st1. Let us see now what happens at the second angle of equilibrium phi st2. If some perturbation causes the ship to incline further to starboard, the heeling arm will be larger than the riding arm, and the ship will capsize. If the perturbation inclines the ship toward port after its disappearance, the riding arm will be larger than the heeling arm, and the ship will incline toward port, regaining equilibrium at the first static angle phi st1. We conclude that the second static angle phi st2 corresponds to a position of unstable equilibrium. The beam wind heeling arm. When a ship is exposed to a beam wind, the wind pressure acts on the portion of the ship above the waterline, and the resistance of the water to the ship's lateral motion, as shown here, exerts a force on the opposite side below the waterlines, as shown here. The equilibrium is achieved when the ship is moving leeward with a speed such that the water resistance equals the wind pressure, and the ship has heeled to an angle such that the moment produced by the forces of weight and buoyancy equals the moment developed by the wind pressure and the water pressure. As the ship heels from the vertical, the wind pressure, water pressure, and their vertical separation remain substantially constant. The ship's weight is constant and acts at a fixed point. The force of buoyancy is also constant, but the point at which it acts varies with the angle of heel. Equilibrium will be reached when sufficient horizontal separation of the centers of gravity and buoyancy has been produced to cause a balance between heeling and riding moments. We use this figure to develop a simple model of the heeling moment caused by a beam wind, i.e. a wind perpendicular to the centerline plane. In this situation, the wind heeling arm is maximal. In the simplest possible assumption, the wind generates a force, Fv, that acts in the centroid of the lateral projection of the above water ship surface and has a magnitude equal to Fv equal PV times AV, where PV is the wind pressure and AV is the area of the above mentioned projection of the ship's surface. Let us call AV sail area. Under the influence of the force Fv, the ship tends to drift, a motion opposed by the water with the force R equal in magnitude to Fv. To simplify calculations, we assume that R acts at half draft, T divided by 2. The two forces, Fv and R, form a torque that inclines the ship until the heeling moment equals the riding moment. The value of the heeling moment in the upright condition is PV times AV times HV plus T divided by 2, where HV here is the height of the sail area centroid above W0 L0 as shown here. The heeling arm in upright condition is calculated using this equation. How does the heeling arm change with the heeling angle? In the case of a flat ship, i.e. for B equals 0, the area exposed to the wind varies proportionally to cosine of phi. In this figure, we show that for a flat ship, the forces Fv and R would act in the center line plane, both horizontally, i.e. parallel to the inclined water line, W phi L phi. Then the lever arm of the torque would be proportional to cosine of phi. Summing up, the wind heeling arm equals to this equation. The wind pressure, PV, is related to the wind speed, VW, by this equation, where CW is an aerodynamic resistance coefficient and rho is the air density. The coefficient CW depends on the form and configuration of the cell area. An average value for CW is 1.2 with a range from 1 to 1.36. Note that the wind heeling arm is proportional to the square of the wind speed. Here we consider the wind speed as constant over all the cell area. This assumption is acceptable for a fast estimation of the wind heeling arm. However, we may know from our own experience that wind speed increases with height above the water surface. Heeling arm in turning. When a ship turns with a linear speed v in a circle of radius RTC, a centrifugal force FTC develops. It acts in the center of gravity, G, at the height kg above the baseline. From mechanics, we know that this force FTC is estimated using this equation. Under the influence of the force FTC, the ship tends to drift, a motion opposed by the water with the reaction R. To simplify calculations, we assume again that the water reaction acts at half draft, i.e. at a height T divided by 2 above the baseline. The two forces FTC and R form a torque whose lever arm is in upright condition is kg minus T divided by 2 as shown here. For a heeling flat ship, this lever arm is proportional to cosine of phi. Dividing by the displacement force, we obtain the heeling lever of the centrifugal force in turning circle. The speed v to be used in this equation is the speed in turning, smaller than the speed achieved when sailing on a straight line path. The turning radius RTC and the speed in turning v are not known in the first stages of ship design. Dynamical stability. Until now, we assumed that the heeling moments are applied gradually and that inertial moments can be neglected. Shortly, we studied statical stability. Heeling moments, however, can appear or increase suddenly. For example, wind force is usually not constant but fluctuates. Occasionally, sudden bursts of high intensity can occur. They are called gusts. As another example, losing a weight on one side of a ship can cause a sudden heeling moment that sends down the other side. In the latter cases, we are interested in dynamical stability. It is no more sufficient to compare riding with heeling arms. We must compare the energy of the heeling moment with the work done by the opposing riding moment. It can be easily shown that the energy of the heeling moment is proportional to the area under the heeling arm curve, and the work done by the riding arm is proportional to the area under the riding arm curve. To prove this, let us remember that the work done by a force F, which produces a motion from x1 to x2, is equal to this equation. If the path of the force F is an arc of a circle of radius r, the length of the arc subtends an angle d phi is dx equals r d phi. Substituting into the above equation, we get this equation. Here m is the moment. A ship subjected to a sudden heeling moment, mh, applied when the roll angle is phi 1 will reach for an instant an angle phi 2, up to which the energy of the healing moment equals the work done by the riding moment. So that a ship subjected to a sudden healing moment, mh, applied when the roll angle is phi 1 will reach for an instant an angle phi 2, up to which the energy of the healing moment equals the work done by the riding moment as shown here. Or we can write based on the arms, right? The healing arm and the riding arm. This condition is fulfilled in this figure where the area under the healing arm curve is A2 plus A3 and the area under the riding arm curve is A1 plus A3. As A3 is common to both areas, the condition is reduced to A1 equals A2. In this figure we marked with phi dyne the maximum angle reached by the ship after being subjected to a gust of wind. An elegant way to find this angle is to calculate the areas under the curves as functions of the heel angle phi, plot the resulting curves, and find their points of intersection. In this figure, we assume that the gust of wind appeared when the ship was in an upright condition, i.e. phi equals 0. As shown in the following figure, the situation is less severe if phi is greater than 0 and more dangerous if phi is less than 0. Stability conditions, a more rigorous derivation. We describe the dynamics of healing by Newton's equation for rotational motion, where J is the mass moment of inertia of the ship and mh a healing moment. The mass moment of inertia is calculated as the sum of the products of masses by the square of their distance from the axis of roll, where yi is the transverse and zi is the height coordinate of the mass mi. Note that here we neglect damping and added mass. We also neglect the coupling of healing with other ship motions. Let us multiply by d phi on both sides of this equation. We obtain this equation. We transform the factor that multiplies j as follows and integrate between an initial angle phi 0 and a final angle phi f. The result is shown here. The left hand side of the above equation in fact represents kinetic energy K. In the position of a stable equilibrium, the potential energy has a minimum, as the sum of potential and kinetic energies is constant in a system such as that under consideration. It is a conservative system. The kinetic energy has a maximum in the position of statical stability. It can be shown that at the point of statical stability, the following conditions exist. The first part shows that at the point of statical stability, the riding arm equals the healing arm. The second part of the equation shows that at the point of statical stability equilibrium, the slope of the riding arm must be greater than that of the healing arm. This is a rigorous proof that the first static angle corresponds to a position of stable equilibrium, while the second does not, as shown here in this figure. Until now, we looked for the angles of statical equilibrium. Let us examine the dynamical phenomena, i.e. the behavior of the healing angle phi as function of time. The conditions for dynamical equilibrium are as follows. The first equation represents the condition of equality of the areas under the riding and the healing arms. Roll period. For small angles of heel and assuming mh equals 0, we rewrite the dynamic equation of roll as follows. We say that this equation describes unresisted roll. We define the mass radius of gyration, Im, by this equation. Thus, the equation describing the roll motion can be written as shown here. Here we can define a new parameter, omega 0, referred to as the roll natural frequency. The roll natural period can be written using this equation. We conclude that the larger the metacentric height, Gm, the shorter the roll period, T0. If the roll period is too short, the oscillations may become unpleasant for crew and passengers and can induce large forces in the transported cargo. Note that the roll period can also be found using this equation, where C is the solid constant and B is the beam of ship. The solid constant can be obtained after the calculation of Gm through inclining experiments, which will be covered later here. Thus, while a large metacentric height is good for stability, it may be necessary to impose certain limits on it. IMO 1995, for example, referring to ships carrying timber on deck, recommends to limit the metacentric height to maximum 3% of the ship breadth. To obtain more comfortable rolling characteristics, many large ships have anti-rolling tanks or fin stabilizers which operate to reduce roll amplitude. Anti-roll tanks operate on the principle of automatic shifting of liquids from side to side out of phase with the ship's rolling. The liquids present a free surface effect problem which must be taken into account when evaluating a ship's stability. Loads that adversely affect stability. Loads displaced transversely. In this figure, we consider that the mass M belonging to the ship displacement delta is moved transversely a distance d. A healing moment appears and its value for any healing angle phi is d times m times cosine of phi. As a result, the ship's center of gravity G moves to a new position, G1, the distance G1 being equal to this equation, and the riding arm is reduced to an effective value as shown here. In other words, if a weight is moved from A to B, as shown here, the ship's center of gravity will also move from G to G1 in a direction parallel to the direction of movement of the shifted weight. We can check that the above reduction occurs when the vessel is inclined towards the side to which the mass M was moved, while the riding arm increases if the ship is inclined towards the other side. Hanging loads. Lifting of heavy weights over one side, as shown in this figure, affects negatively a ship's static equilibrium. In this case, the lifted weight exerts a force at the end of the cable hanging point, regardless of the heel angle or the height to which the load has been lifted. Therefore, the weight of the side lift is considered as an additional weight at the cable hanging point. Therefore, in this case, the center of gravity will shift from G to G1 as illustrated here. In this figure, we consider a mass M suspended at the end of a rope of length L. In this figure, we consider a mass M suspended at the end of a rope of length H. This effect of this mass can be understood as if the center of gravity G moves to a higher position, GV, given as follows. As a result, we use for initial stability calculations a corrected or effective metacentric height. The destabilizing effect appears immediately after raising the load sufficiently to let it move freely. Looking at this equation, we see that the metacentric height is reduced by the same amount that would result from raising the load by a distance h. In other words, we can consider that the mass acts in the hanging point. Lifting of a weight W, in addition to modifying the vertical center of gravity, generates a transverse heeling arm as shown here. Here D is the transverse distance from center line to the end of boom. Free surfaces of liquids. Liquids with free surfaces are a very common kind of moving load. Any engine propeller vessel needs fuel and lubricating oil tanks. Tanks are needed for carrying fresh water. The cargo can be liquid. Then tanks occupy a large part of the vessel. Tanks cannot be filled to the top. Liquids can have large thermal expansion coefficients, and space must be provided to accommodate for their expansion. Otherwise, unbearable pressure forces may develop. In conclusion, almost all vessels carry liquids that can move to a certain extent, endangering thus the ship's stability. A partially filled tank is known as a slag tank. This figure shows a tank containing a liquid whose surface is free to move within a large range of heeling angles without touching the tank top or bottom. Let us consider that the liquid volume behaves like a ship hull and consider the free surface a water plane. Then the center of gravity of the liquid is the buoyancy center of the liquid. Therefore, we use for it the notation B0. B is referring to the center of buoyancy. While the ship heels, the center of gravity of the liquid moves along the curve of the center of the buoyancy around the meta center M. The horizontal distance between the initial position B0 and the inclined position B5 is obtained using this equation. Here, B0M is in fact the metacentric radius. The value of the metacentric radius is obtained as shown here. Here V is in fact the volume of the fluid inside the tank, and I here is the moment of inertia of the water plane. The amount of transverse movement of the center of gravity can be calculated using this equation, which is simplified as shown here. By comparison with the preceding section, we conclude that the effective metacentric height is as shown here, and the effective riding arm can be obtained using this equation. Note that the liquid density rho can be replaced with the specific volume of the liquid, volume to mass, as follows: rho equals 1 divided by delta. Instead of considering the free surface effect as a virtual reduction of the metacentric height and of the riding lever, we can take it into account as the heeling lever of free movable liquids. Its value can be calculated using this equation. The reduction of stability caused by the liquids in slag tanks is known as free surface effect. Two of its features must be emphasized. The mass of the liquid plays no role, only the moment of inertia of the free surface appears in equations. The effect does not depend on the position of the tank. In general, ships have more than one tank, and different tanks can contain different liquids. The destabilizing effects of all tanks must be summed up when calculating the effective metacentric height as shown here in this equation. Here N in fact is the total number of tanks. Note that if the surface of the liquid has reached the top or bottom of the tank, the sign function is substituted with the factor C, as we can see here. The value of C depends on the degree of fullness, the ratio of depth to breadth of the tank, and the angle of inclination, each of which has some influence on the degree to which the motion of the liquid is suppressed. The values of C can be encountered from tables for the tanks that are half full, 95% full, and 98% full. Note that generally, if for all the tanks with liquids with free surface in a ship this equation stands, the value of C in fact approaches the sign of phi, and we can use this equation. Otherwise, the second method based on C must be used. Note that the process of determining the moment of inertia of the surface in a rectangular tank is relatively simple, since the moment of inertia about an axis through the centroid of the surface is given using this equation. The free surface effect can endanger the ship to a negative metacentric height. Therefore, it is necessary to reduce the free surface effect. The usual way to do this is to subdivide tanks by longitudinal bulkheads, such as shown in this figure. Shifting loads. Shifting loads, also called sliding loads, such as grain, coal, and sand, are a very dangerous type of moving loads. Unlike liquid loads, these materials do not move continuously during the ship roll. Shifting loads stay in place until a certain roll angle is reached, and then they slide suddenly. The sides of a mass of granular materials like those cited above are inclined. The angle between the side and the horizontal is called angle of repose, and it is an important characteristic of the material. The angle of repose of most grain loads ranges between 20 degrees and 22 degrees, but for barley it reaches 46 degrees. Let the angle of repose be PR. During roll, the mass of the granular material stays in place until the heel angle exceeds the angle of repose, i.e. phi greater than PR. Then the granular load slides suddenly and its center of gravity moves horizontally a distance xi and up to a distance zeta vertically. We can calculate the change of the center of gravity using this equation. While the ship rolls back, the load does not move until its angle again exceeds the angle of repose. The accelerations induced by ship motions can cause load shifting at angles that are smaller than the angle of repose. The behavior of granular materials is further complicated by settling and by variations of humidity. The stability of grounded or docked ships. Grounding on the whole length of the keel. This figure shows a ship grounded on the whole length of the keel. If local tide lowers the sea level, at a certain draft, the ship will lose stability and capsize. To plan the necessary actions, the ship master must know how much time remains until reaching the critical draft. A similar situation occurs when a ship is laid in a floating dock. While ballast water is pumped out of the dock, the draft of the ship decreases. In this figure, we consider that the draft T descended below the value T0 corresponding to the ship displacement mass delta. Then the ship weight is supported partly by the buoyancy force and partly by the reaction force R. Note that the reaction force R here has the same effect on the GM of the ship as would the removal of a corresponding weight from a position at the vessel's keel. Here, nabla T is the submerged volume at the actual draft T. The ship heels, and for a small angle phi, the condition of stability is as shown here. This equation is obtained by taking the moment of the forces acting on the ship with respect to the keel. The inequality means that the ship has stability if the moment produced by the buoyancy is larger than the moment produced by the ship weight. This equation can be simplified as this one. Here, nabla is in fact the initial displacement volume corresponding to the ship mass delta. For instance, the following figure shows the curve Km and nabla divided by nabla T times Kg as a function of draft. As can be seen, the critical draft in this case is 1.53 meters. Negative metacentric height. The metacentric height Gm can become negative if the center of gravity is too high or if the influence of moving loads is important. Even with a negative metacentric height, ships with certain forms can still find a position of stability a position of stable equilibrium at an angle of heel that does not endanger them immediately. An example is shown here in this figure, where the GZ curve is based on the data of a small cargo ship built in 1958. The solid line here represents the riding arm curve in ballast departure condition. Let us assume that for some reason the center of gravity G moves upward a distance delta kg equals 0.75 meters. The dotted dashed curve represents the quantity delta kg sine of phi, which is the heeling arm in this case, that must be subtracted from the initial riding arm curve. The two curves intersect at approximately 10 degrees and 55 degrees. The resulting riding arm curve is shown in the following figure. The ship finds a position of stable equilibrium at phi equals 10 degrees. She sails permanently heeled at this angle called angle of lull. Looking again at the previous figure, we see that the first intersection of the two curves is possible because the first part of the GZ curve lies above the tangent in the origin. In the second figure here, we can see that if a ship sailing with a positive angle of lull receives a wave, a small gust of wind, or some other perturbation coming from the starboard, she will incline to the port side and stay there at a negative angle of lull. In a seaway, such a ship can oscillate between these two angles of lull. This kind of abrupt oscillation, different from a continuous roll, is characteristics of negative metacentric heights. An angle of lull can be corrected only by lowering the center of gravity, not by moving loads transversely or by filling ballast tanks on the higher side. Her view 1985 proves this in two waves. First, by considering the metacentric evolute, next by examining the riding arm curve. Once, it was not unusual to see that a ship carrying timber on deck sailed out of harbor with an angle of lull. Today, paragraph 413 of IMO 1995 specifies for such vessels that at all times during a voyage, the metacentric height GM should be positive after correction for free surface effects, and even requires that in the departure condition the metacentric height be not less than 0.1 meters. Removal of topside weight is the most effective method of improving stability because it will not only lower the ship's center of gravity but will also in most cases cause the center of buoyancy to move farther to the low side as the ship is inclined. Removal of topside weight are particularly advantageous in improving the stability of a ship that has little freeboard, when the addition of low weight may be completely ineffective in increasing the riding arms at significant angles of heel. In addition, weight removal is generally beneficial in improving the ship's resistance to foundering after underwater damage. Weight and trim calculations. All models of stability require the knowledge of the displacement mass delta and of the height of the center of gravity, vertical center of gravity shown by kg. Stevens' law shows that the ship trim is determined by the longitudinal position of the center of gravity, LCG. The three quantities delta, kg, and LCG are calculated by summing up the masses of all ship components and their moments about the horizontal and transverse plane. The center of gravity of a ship in upright condition is situated in the plane of port to starboard symmetry of the ship, centerline plane. Therefore, the coordinate of the center of gravity about this plane is 0. However, individual mass ship components may not be symmetrical about the centerline plane, and it is necessary to calculate their moments about that plane and ensure that the transverse coordinate y of the ship's center of gravity is 0. It is usual to call the latter coordinate transverse center of gravity and note it by TCG. Thus, we have a consistent notation for the triple of coordinates LCG, VCG, TCG. VCG also shown by KG. Systematic calculations of displacements and centers of gravity are known as weight calculations, and they are covered here. Recent literature and standards deal with masses rather than weights. We follow this trend here, but use the term weight calculation because it is rooted in tradition. Another subject is the calculation of the trim and of the forward and aft drafts. Also, a ship trimmed at large angle can look unpleasant to the eye. Above all, the trim determines the forward and aft drafts and thus affects certain ship functions. For example, the aft draft must be large enough to ensure sufficient propeller submergence and to avoid cavitation. Weight calculations. Weight groups. A vessel is composed of hundreds, sometimes thousands of mass items. To systematize calculations, it is necessary to organize them into weight groups. The first subdivision is into two main sets, light ship and dead weight. The light ship, less frequently known as lightweight, is the mass of the empty ship. It is composed of the hull, the outfit, and the machinery masses, including the liquids in the machinery and various systems, but not those in tanks or storage spaces. The dead weight is some of the masses of crew, cargo, and passengers, fuel, lubricating oil, provisions, water, stores, and spare parts. The usual abbreviation for dead weight is DWT. In simpler terms, the dead weight is the weight that the ship carries. In the first stages of ship design, known as preliminary design, the light ship masses and their centers of gravity are estimated by empirical equations based on statistics of similar ships or are derived from the masses of a given parent ship. For merchant ships, the light ship groups are the hull, the outfit, and the machinery. The classification of warship weight may be somewhat different. As the design progresses by successive iterations, the weight estimation are refined by subdividing the weight groups into subgroups, the subgroups into lower level subgroups, and so on. Trim. Finding the trim and the drafts at perpendiculars. In this figure, we consider a ship initially on even keel. The corresponding waterline is W0, L0. Let us assume that the ship trims, reaching a new waterline, W theta, L theta. If the trim angle theta is small, for normal loading condition, it is always small. The intersection line of the two water lines, W0, L0 and W theta, L theta, passes through the center of flotation, F, of the initial water plane. The midship draft of the ship on even keel, Tm, can be read in the hydrostatic curves at the intersection of the displacement curve and the vertical corresponding to the given displacement. For that draft, we read the moment to change trim, MCT. We calculate the trim in meters as shown here. The trim angle is computed using this equation, and the drafts at the aft and forward of the vessel are computed using these equations. Note that adding any weight to the center of flotation, the trim angle will not change. Determining drafts after change in loading. When a change in loading is contemplated and the existing drafts are known, one can use the following method to determine the drafts after the change is made. This method is suitable when the changes in draft and trim are small and no large initial trim is present. This method involves determining the differences in drafts before and after the change. In this method, the change in loading is reduced to a single equivalent item by adding algebraically the weight and the longitudinal moments of the individual items and dividing the total moment by the total weight to find the distance of the center of gravity of the equivalent item from the reference plane being used. Then, making use of the fact that if a weight is added at the center of flotation, there is no change in trim. It is assumed that the equivalent item is added at the longitudinal position of the center of flotation. This would change the draft an amount equivalent to the added weight divided by the tons per centimeter immersion at each end of the ship, which is generally called the parallel sinkage. It is next assumed that the equivalent item is moved from the center of flotation to its actual position. This would generate a trimming moment equal to the weight of the equivalent item times the distance parallel to the keel from the center of flotation to its actual location. The change in trim would be equal to this trimming moment divided by the moment to trim 1 centimeter. If it is assumed, for example, that the weight is added forward of the center of flotation so that the trim will be by the bow, the increase in draft forward will be equal to the parallel sinkage plus the change in trim multiplied by the ratio of the distance of the center of flotation above the forward perpendicular to the length between perpendiculars. The change in draft aft, which may be negative, will be equal to the parallel sinkage minus the change in trim multiplied by the ratio of the distance of the center of flotation forward of the after perpendicular to the length between perpendiculars. The process of draft calculation is similar to the method explained in the previous section. Navigational drafts. The navigational draft of a ship in any condition is the draft to the bottom of the greatest projection below the waterline of the hull or any appendage. This draft determines the depth of water required for safe navigation. The navigational draft may be increased somewhat over its static value due to settling of the ship caused by forward motion. It is sometimes necessary for a ship to pass through a channel or enter a dry dock in which the depth of water is less than the ship's normal navigational draft. This situation requires a study of the possible adjustments of the load to minimize the navigational draft. This figure shows a ship on which the rudder projects below the line of the keel a distance A and an appendage forward projects a greater distance B. The navigational draft will occur either at A or B. For any given displacement, the navigational draft will be minimized when the drafts at A and B are equal. The slope of the trimmed waterline which will produce this condition is equal to B minus A divided by C with the ship trimmed by the stern. The trim for the minimum navigational draft will be the slope of the waterlines multiplied by the length between perpendiculars LBP or B minus A times L divided by C. Assume that the drafts of the ship in some condition of loading are known and the problem is to reduce the navigational draft to a certain figure based on the channel depth. Assume that the draft at the rudder in this figure exceeds that at the forward appendage. In this case, there is a plane P located in the forward portion of the ship, at which an addition or removal of weight will have no effect on the draft at the rudder. If a weight is added to plane P, the effect on the aft draft may be considered to consist of parallel sinkage, as if the weight were added at the center of flotation, and the effect of the trim produced by moving the weight from the center of flotation to plane P. If these two effects are equal and in opposite directions, there will be no change in draft at the rudder. This may be expressed using this equation, where W is the added weight. Then the plane P can be located by solving for E. This equation applies not only to the rudder but to any point on the ship if D is the distance from the point at which no change of draft is desired to the center of flotation. Note that this equation here is equal to this equation, and as we know, the trim angle is obtained using this equation. Thus, to obtain the change of draft due to trim at the rudder, we can write this equation. Thus, the change of draft at the rudder location can be calculated as shown here. This draft change must be equal to the parallel sinkage in order to make sure that the draft at the rudder does not change. If the weight were removed rather than added, these equations would still apply, since the signs of both sides would be reversed. If the moment to trim 1 centimeter is based on the length between draft marks rather than the length between perpendiculars, the length between draft marks would be substituted for L in the equations. Having determined the optimum trim and the location at which weight changes have no effect on navigational draft, we can reduce the navigational draft by removing weight aft of plane P, adding weight forward of plane P, or both, until the optimum trim is attained. Flooding and damage condition. We expect a ship to survive a reasonable amount of damage, that is, an amount compatible with the size and task of the vessel. More specifically, we require that the ship that suffered hull damage to an extent not larger than defined by pertinent regulations should continue to float and be stable under moderate environmental conditions. Then passengers and crew can be saved. Possibly the ship herself can also be saved by towing to a safe harbor. To achieve survivability as defined above, the ship hull is usually subdivided into a number of watertight compartments. The length of the compartments should be such that after the flooding of a certain number of adjacent compartments, the waterline shall not lie above a line prescribed by relevant regulations. The same regulations specify the number of adjacent compartments that should be assumed flooded. This number depends on the size and the mission of the ship. The reason for considering adjacent compartments is simple. Collision, grounding, or single enemy action usually damage adjacent compartments. Flooding of adjacent compartments also can be more dangerous than flooding of two non-adjacent compartments. Adjacent compartments situated at some distance from the midship section can cause large trim and submerged openings above the deck, leading thus to further flooding. Also, submerging part of the deck reduces the water plane area and can cause a substantial decrease of the metacentric radius. Flooding of non-adjacent compartments, for example, one in the forebody and the other in the afterbody, can produce negligible trim. Then, even with relatively large draft increases, the deck does not submerge, the waterplane area is not reduced, and the metacentric height may not be affected and may be sufficient. If the deck does not submerge, no openings are submerged. The need for international regulations governing the subdivision of the hull into watertight compartments became clear after the Titanic disaster in April 1912. A meeting was convened in London, leading to the adoption on 20 January 1914 of an international convention of the safety of life at sea. The convention is better known under its acronym SOLAS. SOLAS prescriptions cover many aspects of ship safety, among them fire protection, lifeboats and rafts, radars, radio equipment, and emergency lighting. A few definitions. In this section, we introduce a few terms defined in the SOLAS conventions. They are also used by other regulations. The hull is subdivided into compartments by means of watertight bulkheads. Note that increase in these watertight bulkheads results in an increase in the ship cost. Therefore, the subdivision of ships inevitably involves a compromise between safety and cost. The deck up to which these bulkheads extend is called bulkhead deck, as shown here in this figure. After flooding of a prescribed number of compartments, the ship shall not submerge beyond a line situated at this 76 millimeters, about 3 inches, below the top of the bulkhead deck at side, beyond the margin line. In this figure, we see the sketch of a ship subdivided by 4 bulkheads. The 3 water lines WL1, WL2, and WL3 are tangent to the margin line. They are examples of limit lines beyond which no further submergence of the damaged ship is admissible. If the bulkhead deck is not continuous, a continuous margin line can be assumed, such as having no point at a distance less than 76 millimeters below the deck at side. Let us suppose that calculating the volume of a compartment starting from its dimensions, we obtain the value V. There is almost no case in which this volume can be fully flooded because almost always there are some objects in the compartment. Even in an empty tank, there are usually structural members such as frames, floors, and stairs for entering the tank and inspecting. If we deduce the volumes of such objects from the volume V, we obtain the volume of the water can flood the compartment. Let it be Vf. The ratio mu Vf divided by V is called permeability. It is often noted by mu. More correctly, we should talk about volume permeability to distinguish it from a related notion, that is the surface permeability. Indeed, because of the objects stored or located in a compartment, the free surface area is smaller than that calculated from the dimensions of the compartment. 2 methods for finding the ship condition after flooding. There are 2 ways of calculating the effect of flooding. One way is known as the method of lost buoyancy, the other as the method of added weight. The method of lost buoyancy assumes that a flooded compartment does not supply buoyancy. This is what happens in reality. We can imagine that if there is an open communication between a compartment and the surrounding water, the water inside the compartment exercises pressure equal to and opposed to those of the external water. Then the buoyancy force predicted by the Archimedes principle is cancelled by the weight of the flooding water. In the method of lost buoyancy, the volume of the flooded compartment does not belong anymore to the vessel, while the weight of its structures is still part of the displacement. The remaining vessel must change position until force and moment equilibria are reestablished. During the process, not only the displacement but also the position of the center of gravity remains constant. The method is also known as the method of constant displacement, as the flooding water does not belong to the ship. It causes therefore no free surface effect. In the method of added weight, the water entering a damaged compartment is considered as belonging to the ship. Its mass must be added to the ship displacement, hence the term added weight. Following modern practice, we actually work with masses. However, we keep the traditional name of the method, i.e. we use the word weight. Another reason may be the need to avoid confusion with the term added mass. In the method of added weight, the displacement of the flooded vessel is calculated as the sum of the intact displacement and the mass of the flooding water. The position of the center of gravity of the damaged vessel is obtained from the sums of the moments of the intact vessel and the flooding water. Becoming part of the vessel, the flooding water produces a free surface effect that must be calculated and considered in all equations. Note that since the added weight method involves a direct integration of volumes up to the damaged condition water plane, it is just as well adapted of dealing with complex flooding conditions as with simple ones. For greater accuracy, or where complicated flooding configurations are involved, added weight calculations are recommended. To exemplify the above principles, we choose the very simple example of the pontoon shown in this figure. Two transverse bulkheads subdivide the hull into three watertight compartments. In the following two sections, we assume that compartment 2 is damaged and calculate the consequences of its flooding. We choose deliberately a compartment symmetric about the midship transverse plane of symmetry of the pontoon. Thus, the flooding of compartment 2 produces no trim. Also, the compartment extends for the full ship breadth and its flooding produces no heel. The only change of position is parallel sink. Thus, the complex calculations necessary for conventional ship forms, for large trim, or for unsymmetrical flooding do not obscure the principles, and it is possible to obtain immediately a good insight of the processes involved. For the same reasons, we assume that the volume and surface permeabilities are equal to 1. We leave to an exercise the informal proof that taking permeabilities into account does not change the qualitative results. Although based on different physical models, calculations by the two methods yield the same final draft as it should be expected. Moreover, the stability properties calculated by the two methods are identical. If we compare the initial riding moments, the term initial has the meaning where we consider initial stability as a property governing the behavior of the floating body in a small hill range around the upright position. In that range, the riding moment equals this equation. As we are going to see, we obtain by the two methods the same riding moment. In the method of lost buoyancy, the displacement remains equal to that of the intact vessel. In the method of added weight, the displacement increases by the mass of the flooding water. To keep the product MR constant, the other factor GM must be smaller. At the first glance, it may be surprising that the two methods yield different metacentric height. The explanation given above shows that it should be so because the considered displacements are different. What should be kept in mind after reading the examples is that displacement and metacentric height have different significances in the two methods. Therefore, damage stability data should include the mention of the method by which they were obtained. The length of the assumed pontoon is L equals 20 meters, the beam B equals 5 meters, and the draft in intact condition Ti equals 1.5 meters. Let the vertical center of gravity be kg equals 1.5 meters. We first find the data of the intact pontoon. The displacement volume is calculated using this equation. The mass displacement equals to this. The moment of inertia of the waterplane area about the center line equals to this equation, and the resulting metacentric radius is shown here. The height of the center of buoyancy is kb equals t divided by 2, and the metacentric height is calculated using this equation. For small heel angles, the riding moment in intact condition is calculated using this equation. Lost buoyancy. In the method of lost buoyancy, the flooded compartment does not supply buoyancy. As shown in this figure, the buoyant hull is composed only of compartments 1 and 3. After losing the central compartment, the waterplane area is equal to this equation. To compensate for the loss of buoyancy of the central compartment, the draft increases to this value. The height of the central buoyancy increases to t divided by 2. We calculate the moment of inertia of the waterplane as shown here, and the metacentric radius as presented here. Finally, the metacentric height is calculated using this equation, and the riding moment for small heel angles in the lost buoyancy method is given using this equation. Added weight. For this case, see the following figure. Because of the added weight of the flooding water, the draft of the pontoon must increase by quantity delta t. The volume of flooding water equals this value. The additional buoyant volume of the vessel due to parallel sinking is calculated using this equation. To obtain the draft increment, we equate the two volumes as we can see here. Algebraic manipulation and numerical calculations yield this equation. The draft after flooding is calculated using this equation. The volume of flooding water is calculated as shown here, and the height of its center of gravity is equal to t divided by 2. The displacement volume of the flooded pontoon is shown here. We consider the flooding water as an added weight, therefore we must calculate a new center of gravity as shown in this table. The moment of inertia of the damaged waterplane is the same as in the initial intact condition, that is shown here. Then the metacentric radius equals to this value. In this method, the flooding water is considered as belonging to the displacement. Therefore, if there is a free surface, its effect must be calculated. The moment of inertia of the free surface in the flooded compartment equals to this value, and the lever arm of the free surface effect is calculated using this equation. The height of the center of buoyancy is yielded again by dividing the draft by 2. The corresponding metacentric height and riding moment are calculated as shown here. With the mass displacement calculated using this equation, we obtain the riding moment for small angles of heel in the added weight method. The comparison. This table summarizes the results of the preceding two sections. As expected, both the method of lost buoyancy and that of added weight yield the same draft, 1.875 meters, and the same initial riding moment, as we can see here. The displacements and the metacentric heights are different, but their products, delta times gm, are the same. As happens in most cases, the riding moment in damaged condition is less than in intact condition. The curve of floodable length. The naval architects have devised this curve as shown in the following figure. In the lower part of the figure, we show a ship outlined with 4 transverse bulkheads. Above it, we show a curve of floodable length and how to use it. Let us consider a point situated a distance x from the aftermost point of the ship. Let us assume that we calculated the maximum length of the compartment having its center at x and that will not submerge the margin line, and that length is LF, flooding length. In other words, if we consider a compartment that extends from x minus LF divided by 2 to x plus LF divided by 2, this is the longest compartment with the center at x that when flooded will not submerge the ship beyond the margin line. Now we plot a point with the given x coordinate and the y coordinate equal to LF measured at half the scale used for x values. For example, if the ship outline is drawn at the scale 1 to 100, we plot y values at the scale 1 to 200. There were naval architects who used the same scale for both coordinates. However, there is an advantage in the procedure preferred by us, plotting in this way all XLF pairs. We obtain the curve marked 1. This is the curve of floodable length. Now let us check if the middle compartment meets the submergence to the margin line requirement. Counting from aft forward, we talk about the compartment limited by the second and the third bulkhead. Let us assume that this is a machinery compartment with permeability mu equals 0.85. Therefore, within the limits of this compartment, we can increase the floodable length by dividing them by 0.85. The resulting curve is marked 2. Let us further assume that we are dealing with a ship subject to a 2-compartment standard, factor of subdivision f equals 0.5. Then we divide by 2 the ordinates of the curve 2, obtaining the curve marked 3. This is the curve of permissible length. On the curve 3, we find the point corresponding to the center of the machinery compartment and draw from it 2 lines at 45 degrees with the horizontal. The 2 lines intercept the baseline at A and B. Both A and B are outside the bulkheads that limit the machinery compartment. We conclude that the length of this compartment meets the submergence criterion. Indeed, as the y coordinate of the curve of floodable length is equal to half the length LF, we obtain on the horizontal axis a length AB equals LF divided by mu times F, factor of subdivision. That is the permissible length. It is larger than the length of the compartment. To draw the lines at 45 degrees, we can use commercially available set squares, triangles. If we plot both x and y values at the same scale, we must draw check lines at an angle equal to arctangent of 2. With respect to horizontal. There are no set squares for this angle. The use of these inclined lines is important to identify whether or not the length of a compartment or a combination of compartments is greater than the permissible length of the floodable length. Based on this figure, we can identify the properties common to all curves of floodable length and give more insight into the flooding process. 1. At the extremities, the curve turns into straight line segments inclined 45 degrees with respect to the horizontal. Let us choose any point of the curve in that region, drawing from it lines at 45 degrees, that is descending along the first or the last curved segment. We reach the extremities of the ship. These are indeed the limits of the floodable compartments at the ship extremities because there is no vessel beyond them. 2. The straight lines at the ship extremities rise up to local maximum. Then the curve descends until it reaches local minima. Usually the ship breadth decreases toward the ship extremities and frequently the keel line turns up. Thus, compartment volumes per unit length decreases toward the extremities. Therefore, floodable lengths in that region can be larger, and this causes the local maxima. 3. As we go toward the midship, the compartment volumes per unit length increase, while still being remote from the midship. Flooding of such compartments can submerge the margin line by trimming the vessel. Therefore, they must be kept short, and this explains the local minima. The curve has an absolute maximum close to the midship. Flooding in that region does not cause appreciable trim, therefore floodable length can be larger. The inclining experiment. It is usual to carry out the inclining experiment a short time before the completion of the ship. The vessel must float in calm water, and the work must be done while no wind is blowing. The number of persons aboard should be limited to that strictly necessary for the experiment. Their masses and positions should be exactly recorded. Tank fillings and free surfaces in tanks should be well known. Free surfaces should not reach tank bottoms or ceilings for the expected heel and trim angles. All draft marks should be read, i.e. forward, at midship, at stern, both on starboard and on port side. This procedure minimizes errors due to small waves. The water density should be read at several positions around the ship. This figure shows a common setup for the inclining experiment. A pendulum which is hung at A. The pendulum is immersed in a water tank that serves as an oscillation damper. A mass P is displaced transversely a distance d. The resulting heel angle, assumed small, is given by this equation. The deflection of the pendulum line is measured on a graduated line R1, R2, and is used to calculate the tangent of phi. A recommended practice is to displace the mass once to starboard and measure the tangent, then to port, and again measure the tangent. The final tangent is assumed to be a mean value of these two tangents. It is also recommended to move the weight slowly to avoid inducing a roll. The masses used for inclining the vessel should be chosen so that the heel angles fall within that range in which this equation is applicable, which is smaller than 3 degrees. When analyzing the results of the inclining experiment, the above equation is written as shown here. The interpretation of the results of inclining experiments requires the knowledge of the displacement, delta, and of the height of the metacenter above the baseline Km. If the trim is small, one can read the desired values in the hydrostatic curves, entering them with the measured mean draft Tm as input. If the trim is not small, one can use the Bond-Gene curves or a computer program for hydrostatic calculations. An example result obtained from inclining experiment for a ship is shown in this figure. The figure depicts the tangent of inclination with respect to the heeling moment obtained from several experiments. Note that this plot is linear. Based on this result, it is possible to calculate the GM value using this equation. Static stability of floating wind turbines. The restoring in case of floating wind turbines is achieved through 3 mechanisms: water plane area, ballast, and the mooring system, which are described further in the following sections. Restoring from water plane area. Restoring from a structure's water plane area is provided by the moment that the structure's water plane area makes about the structure's center of rotation. Water plane area moment about x and y axis are given by the equations below, and the effect of water plane area moment on the structure's restoring is shown in this figure. S in this integral represents the water plane area surface when the structure is not offset in pitch or roll. The dotted line on the structure in this figure represents the structure's water plane. For small angles of deflection in pitch, the shape of the water plane is relatively constant. When the structure is perturbed in pitch, One side of the structure is submerged and the other side is elevated from the water. The submerged side experiences an increase in buoyant mass and a larger volume of water is displaced on that side. The other side experiences a decrease in buoyant mass and a smaller volume of water is displaced on that side, equal to the increase on the other side. These increases and decreases in buoyant mass results in increases and decreases in buoyant force delta F. The moment the water plane area makes about the y-axis determines the moment that results from these delta F forces. This moment opposes the moment exerted on the body to displace it in pitch and results in a restoring moment. This restoring moment is given by the following equation. Employing the small angle approximation, these equations reduces to the following expressions. For a cylinder, as shown in this figure, or other axisymmetric bodies, restoring in pitch is equal to restoring in roll. This is because the water plane area is symmetric about the x and y axis and thus creates an equal moment about both axes. Restoring from ballast. Restoring by ballast is achieved when enough ballast is added to the structure to lower the center of gravity to a location below the center of buoyancy. Restoring is then provided by the vertical separation between the structure's center of gravity and the structure's center of buoyancy. The restoring effect due to ballast then combines with the restoring effect of water plane area to form hydrostatic and inertial restoring. Hydrostatic and inertial restoring is illustrated in this figure. As shown in this figure, when the system is offset in pitch, the buoyant force acting on the center of buoyancy creates a moment about the origin, and the gravitational force acting on the center of gravity creates a moment in the opposite direction about the origin. For a freely floating structure, the gravitational force is equal to the buoyant force, and the vertical distance between the center of buoyancy and the center of gravity results in a net moment that has the tendency to restore the system to its vertical position when the system is offset in pitch. When the system is offset in pitch, the water plane area causes the center of buoyancy to shift toward the side of the structure that is submerged. This effect is captured by the water plane area component of restoring discussed in the previous section. The combined hydrostatic and inertial restoring moment is given by the following equation, where mg, mb, z, cg, z, cb represent the gravitational and buoyant masses and the centers of gravity and buoyancy respectively. Employing a small angle approximation again, this moment reduces to the following equation. Restoring from mooring lines. Restoring by mooring lines is provided by the moment that the mooring lines exert on the structure due to a displacement in pitch. The effect that the mooring lines have on the restoring properties of the structures is dependent on the mooring line configuration. For slack mooring systems with catenary mooring lines, the restoring in pitch can be crudely modeled as the product of weight of the lines in water and the draft of the fairleads. The levels of restoring in pitch provided by catenary mooring systems are negligible compared to the amount of restoring required for structures capable of supporting large wind turbines. The restoring in pitch from catenary mooring lines is therefore taken as zero, and the structure itself is required to provide adequate restoring. For tension leg mooring systems, the magnitude of restoring provided is dependent on the stiffness of the mooring system and the radial location of the fairleads where the mooring lines attach to the structure. The restoring coefficient in pitch provided by a tension leg mooring system is given by this equation. In this equation, EA tethers is the product of the elastic modulus and the sectional area of the tethers. L tethers is the unstretched length of the tethers. R is the cylindrical radius. L leg is the length of the leg to which the line is attached. F tethers is the total force exerted by the tethers, and T is the cylinder draft, or the vertical distance to the tether fairlead. The equation above for restoring provided by tension leg mooring system shows that the restoring coefficient in pitch is dependent upon the elastic properties of the mooring system. Note that considering that assumption of infinite stiffness of the mooring lines prevents any significant motion in pitch, roll, and heave, and the platform's motion are therefore limited to surge, sway, and yaw, or the motions in the horizontal plane. The mooring system must then be designed to adequately limit motions in these modes. Therefore, considering infinite stiffness prevents any significant motion in pitch, roll, and heave, which are the motions in the vertical plane, but the mooring system must limit the motions to reasonable values in surge, sway, and yaw, which are the motions in the horizontal plane. A tension leg mooring system must also maintain reasonable tension in all of its tethers. With the steady state wind force acting in the positive x direction, the tension in upwind tether increases and tension in the downwind tether decreases to provide a balance of forces and moments. And this operational scenario is shown in this figure, where FTI stands for the tension force in tether I, where tethers are numbered counterclockwise starting at a leg that corresponds with the positive x-axis. The initial tether tension must be chosen to ensure that the tension in the upwind tether does not exceed the maximum allowable tension, and the tension in the downwind tether does not drop below the minimum allowable tension. To summarize, the tether tension for this system must therefore fulfill two requirements. First, the tethers must provide sufficient restoring in surge to adequately limit the steady state offset in surge. Second, the tension of the windward tether must never exceed the maximum allowable tension, and the leeward tether must never go slack or fall below the minimum allowable tension at any point during operation. Under steady state conditions, the platform will achieve its steady state displacement in surge. At this displacement, the tethers will form an angle with the vertical, shown as theta in this figure. The tethers must be of sufficient tension to provide adequate restoring to limit this angle to about 5 degrees to prevent the system from experiencing highly nonlinear restoring and displacement. Restoring in surge caused by the tethers is related to the tether tension and length through the following equation. Restoring results in a steady state displacement through the following relation. An initial limit for the tether tension is reached by limiting the system's steady state displacement. This tension must also satisfy the second requirements for the operational line tension. In operating conditions, the tension in each line is found by solving a balance of forces and moments for the tensions. Total restoring and the restoring coefficient in pitch. Contributions to restoring from waterplane area, ballast, and mooring lines combined to result in the total restoring properties of a floating platform. The restoring coefficient is defined to characterize the total restoring properties due to the system's offset in pitch. As developed in the previous sections, the restoring moment that the structure experiences due to its geometry and its offset in pitch is summarized here. This equation shows that the restoring moment that the structure experiences is proportional to the offset in pitch. The restoring coefficient is that coefficient of proportionality and is given by this equation. For a surface piercing cylinder with a radius r, the equation above is evaluated to give the following expression. Conceptually, these three restoring mechanisms can be summarized by three extreme structures: a semi-submersible platform or a barge representing restoring by waterplane area moment, a ballasted deep drafted spar representing restoring by ballasting, and a tension leg platform TLP that represents restoring by the mooring system as shown here. These restoring methods and their representative structures are shown in this figure, which represents the stability triangle, where the sum of the three contributions, each one going from contributing 0 to 100% of the total stiffness, amounts to the total hydrostatic stiffness of the system. If the body is freely floating, the buoyancy to weight ratio is equal to 1, and therefore if the CG is below CB, the contribution of this term to the restoring moment is positive, while if CG is above CB, the contribution is negative. This is an important consideration for floating wind turbines, since even if the mass of the wind turbine system, rotor plus nacelle plus tower, is usually smaller than the mass of the support structure, the CG of the wind turbine can be very high and push the total CG above the CB. In reality, no structure can perfectly isolate a single restoring mechanism. Instead, structures achieve their restoring through a combination of these mechanisms. This is the end of this video. I hope you found this video useful. Please let me know what you think about this video by leaving a comment in the comment section. Thank you for watching the video, and for further upcoming videos, please subscribe to this channel.